Welcome back to the deep dive. This is where we take a whole bunch of sources and really boil them down to the essentials for you. Think of it as your shortcut to getting up to speed.
Exactly. And today we're diving deep into a brand new study, just out April 2025. It's called PaperBench, Evaluating AI's Ability to Replicate AI Research.
Right, and the core idea basically is to see how well AI agents can actually reproduce cutting-edge machine learning research papers.
Yeah, so if you're interested in the future of AI, especially how it might be used in, actual research, this analysis gives a really clear look at current capabilities and also the limitations.
We're going to break down how they did this evaluation, what the main findings were, and importantly, what it all means for the progress of artificial intelligence.
And just a quick reminder before we jump in, to keep exploring topics in machine learning and AI, we invite you to subscribe to the AI and Data Insights newsletter and follow us on LinkedIn and X.
Okay, so let's get into it. What was the main motivation behind creating PaperBench in the first place?
Well, the really exciting part here is the possibility. The idea that autonomous AI agents could eventually replicate ML research. I mean, that could seriously speed up progress in the field.
Right, accelerate innovation.
Exactly. But an idea that powerful needs careful study. For safety reasons, too.
Yeah.
PaperBench basically came about to do that kind of thorough evaluation.
I see. So how does it actually work? How did they test these AI agents?
So what they did was take 20 papers from a top conference, ICML 2024, specifically the spotlight and oral presentations. They gave the AI agents the full content of these papers.
Okay, and the task?
The task was to replicate the empirical contributions, the experiments, completely from scratch.
From scratch. Wow, that sounds...
Oh, it is. They
Yeah.
had to understand the paper, develop the necessary code, run the experiments, and troubleshoot any issues that came up. I mean, keep in mind, this is something that takes human experts days of work.
Right. Days of intense work. And were these papers all on similar topics?
No, they covered a good range, 12 different ICML topics, actually. Things like deep reinforcement learning, robustness, probabilistic methods. So it tested the AI across different areas.
Okay, so once the agents attempted the replication, how did they measure success? How did the evaluation work?
This is where it gets really interesting. To make it rigorous, they created manual rubrics for each of the 20 papers. And crucially, they co-developed these rubrics with the original authors of the papers.
Ah, collaborating with the original authors. That makes sense for accuracy.
Exactly. It ensures the evaluation criteria were, actually correct and reflected what really mattered for replicating that specific piece of research.
And how detailed were these rubrics? You said manual rubrics.
Super detailed. Each rubric was hierarchical, breaking the huge task of replication down into much smaller, gradable subtasks. All in all, PaperBench had something like 8,316 individually gradable tasks.
Whoa, over 8,000. That really shows the granularity they were going for.
Yeah, it gives you a sense of the complexity hidden in just one research paper.
And did the agents have any restrictions? Like, could they look up the original code?
Nope. That was a key rule. The agents were not allowed to use or even see the original author's code. The whole point was to test their ability to code and run complex experiments themselves from the ground up.
Okay, so how was the execution handled when an agent produced code?
Right. So once an agent finished its attempt, its code was moved to a clean virtual machine running Ubuntu 24.04 with GPU access.
Standard setup.
Yep. And then a specific script, reproduce.esh, had to be the entry point to run everything needed to generate the paper's results. Kind of like starting fresh in a controlled lab environment.
Gotcha. And then they compare the outputs.
Exactly. They checked if running that script actually managed to reproduce the results reported in the original paper using those detailed rubrics we talked about.
Let's talk a bit more about that scoring system. You mentioned the rubrics were like requirement trees. How did that work?
Correct. Think of each rubric as a tree structure. The leaves, the smallest parts, had binary criteria: pass or fail. Did it meet this specific requirement? Yes or no?
Simple enough at the leaf level.
Right. Then, the parent nodes higher up got a score that was a weighted average of their children's scores. This process repeats all the way up to the root of the tree.
And the score of that root node was the final result.
That's it. The root node score became the final replication score for that particular attempt. It basically measured the proportion, weighted by importance, of all the rubric requirements the agent managed to satisfy.
You mentioned 3 types of requirements at the leaves: result match, execution, and code development. Can you break those down quickly?
Sure. Result match nodes checked if running the agent's code actually produced a specific result from the paper. So they'd look at the output files, the logs, the reproduce.esh script. For example, do the F1 scores show the same trend when a term is removed?
Okay, focuses on the final outcome. What about execution?
Execution nodes checked if a particular step or process actually ran when executing reproduce.sh. Here, they'd look at logs in the script, but also the source code itself, like did the code to evaluate the prior free method run and were F1 scores logged?
And code development.
These nodes looked directly at the agent's source code to see if it contained a correct implementation of something specific. This allows for partial credit even if the whole execution failed later. An example might be, was code written to generate predictions using BART0 large on the test set?
Ah, I see why they included execution and code development. Even if the final result isn't matched, you want to give credit for getting parts of the process right.
Exactly. It helps ensure that agent performance on PaperBench can improve incrementally. You recognize the partial successes along the way, even if full replication isn't achieved immediately.
I also read about something called Judge Eval. What was that, and why did they need it?
Right, Judge Eval. The thing is, evaluating even one replication attempt could take a human expert many, many hours given the complexity. Just reading the code, running it, checking outputs against the rubric.
Yeah, that sounds incredibly time-consuming.
It is. So to make evaluation scalable, they created Judge Eval. It's an auxiliary benchmark specifically designed to measure how accurate large language model-based judges are. Could an automated judge, using an LLM, do a reliable job, or at least part of the job?
Ah, okay. Using AI to help evaluate the AI replications. Makes sense for scaling up. So what were the main findings when they actually tested these AI agents on PaperBench?
Well, the top-performing agent they tested was Claude 3.5 Sonnet, the newer version, using an open-source support framework or scaffold. It achieved an average replication score of 21.0%.
Only 21%.
Hmm.
That does sound quite low.
It really highlights how challenging this task is, doesn't it? They also did a test with human ML PhDs, giving them the best of 3 attempts on a subset of 3 papers. The humans reached 41.4% after 48 hours.
Okay, so about double what the best AI managed. How did the AI compare in that same subset?
On that specific subset, the O1 model, which is another strong model, scored 26.6%, so still significantly behind the human experts given a decent chunk of time.
Interesting. And what about PaperBench Code Dev, the version that only looked at the code itself?
Right, the lighter version. On that, O1 actually reached 43.4%. This suggests the models might be somewhat better at the coding part itself, but struggle more with the full execution and results validation.
So, summing up the contributions of the study, what were the key outputs?
The main contributions were really the PaperBench benchmark itself, with its 20 papers and author-approved rubrics, the automated evaluation workflow using those LLM-based judges, the lighter-weight PaperBench code dev, the Judge Eval benchmark for assessing those judges, and finally the actual evaluations of several frontier AI models on PaperBench.
Got it. PaperBench Code Dev sounds like a useful tool for quicker, maybe less comprehensive checks.
Exactly. Since it only focuses on code evaluation, it avoids the need for expensive GPU execution, making it more accessible. Though interestingly, the authors noted that performance on code dev was only weakly correlated with performance on the full PaperBench, so it doesn't tell the whole story.
You mentioned earlier that creating the rubrics was really difficult. How long did that take?
It was apparently a huge effort. They said it took several weeks per paper, working closely with the original authors. It just underscores how complex it is to precisely define what successful replication even means for a given paper.
And how do they manage the large-scale evaluation? You mentioned the LLM judge, Simple Judge. How did that work practically?
Yeah, to scale things up, they implemented Simple Judge using the O3 mini language model. It was given the paper, the rubric, and the agent's submitted code for each evaluation criterion.
And the cost? Was it efficient?
Well, they estimated the cost using O3 Mini was about $66 in OpenAI API credits per submission evaluation.
$66 per evaluation still sounds like quite a bit.
It does, but it's significantly cheaper and faster than having a human expert do the same detailed check. They also mentioned that for the simpler PaperBench code dev, the cost dropped to around $10 per evaluation.
Okay. And where were the experiments run? Any specific rules to ensure fairness?
They were run in Docker containers with access to an A10 GPU. And yes, several important rules for fairness. Agents couldn't use the original author's code. Internet access was restricted using blacklists to prevent finding existing replications online. And they were given necessary API keys, like for Hugging Face, so that wasn't part of the challenge.
I also saw they used different the scaffolds, basic agent and iterative agent. What were those, and how did they affect the results? Like, what does scaffolding mean here?
Think of the scaffolds as different ways of guiding the AI agent through the task. Basic agent was a simpler loop, while iterative agent was designed to keep the agent working on the problem for the full time allowed, prompting it to take one step at a time towards replication and preventing it from stopping early.
Different strategies for the AI.
Right. And the results showed that the iterative agent significantly boosted scores for models like O3 Mini and O1. But interestingly, it actually hurt the performance of Claude 3.5 Sonnet.
Really? So the scaffolding matters, and it depends on the model.
Exactly. It shows how sensitive these models can be to the prompting and the overall approach used to guide them.
And that comparison of human versus AI performance over time on the subset of papers, what did that reveal?
What they saw was pretty fascinating. Initially, the O1 agent generated code faster, actually outperforming the humans in the first few hours.
Oh, interesting. Faster start for the AI.
Yeah, but after about 24 hours, the human experts started to pull ahead and eventually surpassed the AI. It suggests that while AI might be quick at initial code generation, humans are currently better over longer horizons at planning, iterating, and refining their replication attempts. The AI scores tended to plateau after the first hour or so, while the human scores kept climbing, albeit slower initially.
So wrapping up this section, what's the main takeaway about the current state of AI systems for replicating ML research?
The bottom line, really, is that despite showing some capability, especially in implementing methods and validating some results, current AI systems are still quite far from being able to competently replicate the full range of tasks needed for successful ML research replication. That 21% score for the best agent on the main benchmark really drives that home.
Okay, we're nearing the end of our deep dive today. Could you quickly summarize the key points we've covered?
Sure. We looked at PaperBench as a new, challenging benchmark designed to test AI agents' ability to replicate cutting-edge ML research. We explored its rigorous evaluation methodology using detailed, author-approved rubrics. We also discussed the use of LLM-based judges for scalability and the initial findings which show, well, the current limitations of AI agents in handling this complex task.
And we underscored how important these kinds of evaluations are for actually understanding and tracking the progress of AI autonomy in scientific research, especially considering how tough even the human PhDs found the task. What does that tell us?
Exactly. And that leads nicely into a final thought, drawing from the paper's conclusion. While these initial results show significant limitations, the fact that there is non-trivial progress in implementing and validating methods suggests a promising future for improving AI capabilities in research.
Right, there's potential there, even if it's not fully realized yet.
It really poses the question for the ML community. How can we leverage these advancements while also considering the implications for the pace of innovation and, crucially, the need for deep understanding and appropriate safety measures?
That's a really vital question. What aspects of AI research do we think will be hardest to automate? And how can benchmarks like PaperBench help us prepare for a future where AI plays an increasingly significant role in scientific discovery? Something to chew on.
Definitely. And to keep exploring these fascinating topics, we'd once again invite everyone to subscribe to the AI and Data Insights newsletter and follow us on LinkedIn and X.
Thanks for joining us on this deep dive. We'll catch you next time.